Hello. In the previous lecture, we started discussing public key cryptosystems or the so called asymmetric ciphers, and we started with the most famous public key cryptosystem, which is called RSA cryptosystem. Now, in this lecture, we will continue the discussion on RSA, but we will be concentrating on the computational issues, because when we did RSA, we said okay fine, this is how to get the keys and this is how to encrypt, this is how to decrypt, and we were seeing at each place that there are certain computations that we have to do which do not look very easy per se. So, for example, let us go back to RSA. Our starting point here is two very large primes. The first question is that how are we going to get these large primes? That is something that we will discuss in the lecture after this one. So, the first line will be discussed after this lecture, not in this lecture, but then there is a question that if we have to multiply two large primes, how easy or difficult it is to do that. Now, for that we can start thinking. For example, if you have a number, let us say 6 is greater than 2 to the power 2 and less than 2 to the power 3. We know that if we take log to base 2 of 6, then it is going to lie between 3 and 2. It will be a fraction between 3 and 2, and so if we take the ceiling of log to base 2 of 6, then I will get 3, and this means that I need at least 3 bits to represent 6. Now, so if I have a large prime P and another large prime Q, then by log I mean log to base 2. So, log P ceiling is the number of bits that we require to store P, and log Q ceiling is the number of bits required to store Q, and they are large. I mean, they are like probably 600 bits long, and we are also assuming here is that more or less P and Q are of the same order, that is to say they are of the same size, and therefore we are also assuming that these two are same. So, I will be referring to this size by log P. Once we know this, then we can get some idea of the difficulty in computation of the product PQ. So, right now we do not have the idea of the difficulty of finding the primes, but let us assume that we have got the primes. If we have the primes, then we would like to multiply them, and what I claim is that the multiplication will take around ceiling of log P square steps or elementary operations plus something, or we can just say a small, probably a small constant multiple of this. Another thing that I am going to do in this lecture is to drop the ceiling sign. So, I will be simply writing log 2 to p and square, or I may just be writing log p square, and assuming that if I am not told otherwise, then log p is always base 2. So, we have to multiply, and we will see that if we have two numbers written in binary, suppose 1101 and 1011, the question is how to multiply. The answer is not difficult, we just multiply as usual multiplication. So, I will write 1 1 here, because 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1, and 1 into 1 is 1, and then I cross out the rightmost column and start from here. This is a usual multiplication, then again it is 1 0 1 1. So, alright, and then I cross out again this portion, now it is 0. So, I know it is 0 0, well after that 0 0 1 0, sorry 0 0, it is by 0. So, it is all zeros. So, 0 0 0 0, then cross out this column and I am going to get 1 0 1 1 and do this, and then I have to sum. Now, how many times I have to sum? I have to sum the number of times, number of bits that I have in these numbers. So, anyway I can sum them up and write the product. This is the product. The question is that how many comparisons did I have to make, and that is, this is a 4-bit long integer, 4-bit, and this is also 4-bit long. So, I had to make 4 into 4 comparisons in these steps, and I generated 4 rows, and I will have to add them up, or I could have added on the fly and gotten this number. So, anyway the dominating part of this computation is 4 into 4. So, I know that I need something close to 4 into 4 many comparisons to make, and a little more. Now, if we have in general two numbers, as we have seen here, that I can talk about the number of bits that are required to represent them. So, the multiplication can be done in roughly this many steps, log 2 square. So, that is what I have written in the first line, it is here. So, that is how to compute n. We have to anyway compute n to implement RSA, and after that we have phi n, and phi n is p minus 1 into q minus 1. It is reasonable to believe that p and p minus 1, they are of the same order and they require the same number of bits. If that is so, then for phi n we will require the same number of steps, that is log p square. And now we come to the computation of GCD, because we have to decide whether A is co-prime to phi n. Now, in the algorithm, when I told that okay, you have to find B and then you have it which is co-prime to phi n and then compute A, and while writing I am writing here for the complexity issues, I am starting with A and I am telling that I have to find B, both are equivalent anyway. So, I come over here. So, I have to decide whether A is co-prime to phi n or B is co-prime to phi n. As I said, they are same, so I fix A. So, I want to decide whether A is co-prime to phi n, and to do that I have to compute the GCD of A and phi n. Now, before starting to calculate the complexity of GCD computation of A and phi n, I would like to point out that this is exactly where the security of RSA lies. So, we have to decide whether A is co-prime to phi n. Now, what is phi n? We know that phi n is equal to phi of p q, which is equal to p minus 1 and q minus 1. Now, if we do not know the factorization of n, then we cannot get this value very easily. We can of course get this value by starting from 1, going up to n minus 1, because we know n, and checking each time whether the greatest common divisor is equal to 1 or not, and if it is 1, increment a counter. In that way we can get phi n, but if it is if n is a number which is a product of two 600 bit primes, then it is going to be very large and the computation will not end. So, I will not be able to know phi n, and if I do not know phi n, then also the question is that how will I know B? Okay. So, if I do not know phi n, so this is where the problem lies with RSA. I mean, in the sense that this is where the security of RSA lies, and this is the problem that is difficult to solve. But now we are assuming that we are the people who are setting up the key. So, therefore, we know phi n. Now, we know phi n, so we have to compute the GCD. GCD computation is easy. GCD computation is done in school, and that is the technique that we will be using. So, what is it like? So, suppose we take phi n equal to R1 and A is equal to R2. Then what we can do is we start off with R1 is equal to Q2 R2 plus R3, then R2 is equal to Q3 R3 plus R4. So, we can go on like this, and ultimately we will have the GCD. So, if we do it as we do in school, so it will be something like this. The first I am taking R2, I am dividing R1 by R2. So, I will get a quotient Q2, I will get something over here I do not know, but I will subtract and get R3, and then with R3 I will divide R2 by R3, then I will get a quotient Q3, and I will get essentially R3. Yeah, of course, this is something that I know, I should not say that I do not know. So, this is R3 Q3. So, of course, I can write it here, that is R2 Q2, and I will get R4 and go like this. So, at one point of time I will coming to something like, let us say Rk, I will say that there is no remainder. So, Rk minus 1 is completely divisible by Rk, and this Rk becomes the greatest common divisor. This is the rule that goes on. And we also know that if we look at this rule, these successive remainders decrease in this chain strictly, and that is why we know that we come to a greatest common divisor. Now, the question is that how many steps we have to go through to come to the greatest common divisor. Now, why it is important? Now, if you look at the complexity of computation at each side, at each step we have a division, and we know that division can be done with the same complexity as multiplication, and we know that multiplication is essentially equal to the complexity of multiplication is square of the number of bits involved in individual numbers. In this case, the largest number involved is phi n, so that is p into q. So, the number of bits involved is going to be 2 times log of p. So, I know that each step I will need around 2 times log of p, at most many steps for multiplication, it may be much less, but the question is how many times I have to do this. 2 times log of p square for multiplication. The question is how many times we have to do it. Now, if it is kind of decreasing 1 by 1, then it is going to be very large, because our numbers involved are very large numbers. So, for example, this one is potentially something which is 1 less than R2 to 1. So, R3 we know by division algorithm that it is of course less than R2 and greater than or equal to 0, but it can be just, of course it can be R2 minus 1, it is possible. But then in this chain it is quite possible that they decrease 1 by 1, but this A, that is R2, can be a very large number, of course, because A is chosen at random from Z sub PQ. So, it is a very large number, but then we will have a many steps to go, and each step we have a square of a log, but anyway it may be as large as the number itself. And this is where we have a very interesting fact. There is a number theoretic argument which says that we really are not going to go that far or that many times. It says that this algorithm terminates much faster than whatever we may think is the worst case, and that argument is here. So, let me explain this. So, what we have done here is to cut a small portion of this sequence of calculations. So, we will do that over here. So, I will write on the blackboard as well. So, let us first look at the slides at the beginning, and then we will discuss this. So, what we see here is that Ri minus 1 is equal to Qi Ri plus 1, of course, and then you have a cyclic shift. Ri goes to the left hand side, Ri equal to Qi plus 1 into Ri plus 1 plus Ri plus 2, and we know that this kind of inequalities will be satisfied, that Ri plus 1 is strictly less than Ri and Ri plus 2 is strictly less than Ri plus 1. So, we first concentrate on this inequality. If you look at this inequality, let us write it over here, is 0 less than or equal to Ri plus 1 is strictly less than Ri. Okay, fine. Suppose this is Ri and this is 0, and Ri plus 1 is somewhere here, we do not know where it is right now, but there is of course something we know, that is half of Ri. Yeah. So, one thing is certain, that Ri plus 1 is either this side or this side. Let us assume that it is this side. So, that is what we have written here, that Ri plus 1 is greater than half of Ri. Now, if that is so, then we come to the next step, that is Ri plus 2 is equal to Q Ri plus 2 is equal to Ri minus Qi plus 1 into Ri plus 1. That is of course true, because I have got the second line. So, I am writing like this: Ri plus 2 is equal to Ri minus Qi plus 1 Ri plus 1. Now, the question is that what is the minimum value possible for Q, whatever be the division. Now, of course, Q cannot be 0, because if Q is 0, then Ri is equal to Ri plus 2, which is not possible. So, Q will start from 1 onwards. So, Q is greater than or equal to 1. Now, I have got a difference here. I know that Q is greater than or equal to 1. If I put the smallest possible value of Q, then I will get something large, something greater or equal to something greater than or equal to Ri plus 2, and that is what we have got over here. Yeah. So, Ri minus Ri plus 1 is greater than or equal to Ri plus 2. The question is why? Because I know that Qi plus 1 is greater than or equal to 1. So, if it is greater than or equal to 1, if I put 1, I will get something greater or equal. So, this is Ri minus Ri plus 1. But now, if you look at this, we already have assumed that Ri plus 1 is strictly greater than 1/2 of Ri. We plug in over here, this chain continues with a strict inequality here, because you have a strict inequality over there, and therefore, eventually we will come to a scenario like this, that Ri plus 2 is strictly less than half of Ri. So, here I will have a strict inequality 1/2 of Ri, and which is equal to Ri, 1/2 of Ri. Now, this means that this means that if Ri plus 1 is on this side of the half of this range, then the right half of the range, then Ri plus 2 is strictly less than 1/2 of Ri. Now, suppose Ri plus 1 is on this side. If Ri plus 1 is on this side, the argument is somewhat easier. So, we already know that Ri plus 1 is Ri plus 2 is strictly less than Ri plus 1, and we are being told that this is less than or equal to half of Ri. So, combining these two things, we will have the same result, that Ri plus 2 is strictly less than 1/2 of Ri. That means, in terms of binary representation of integers, the the number of bits required to store Ri plus 2 is 1 less than the number of bits required to store Ri. So, if you jump 2 steps, you jump by half of the quantity, the remainder becomes less than half of the original, and the number of bits required becomes 1. So, you will basically be going to at most the number of bits that are there in the initial remainder, that is something something that you get in the first line, and that remainder can never exceed the initial divisor, that is A, that is whose number of bits is bounded above by log p. So, you are not going to go more than log to base 2 p many times. So, this is something that we know, and then the people who know extended Euclidean algorithm knows that this is enough. Each time we can store something and ultimately we can compute the inverse B, but we do not assume even that. We have seen in our previous lectures that if I can do the chain once, I can move backward in the chain and find out the inverse. We have done it. So, maximum number of times I have to go back and forth is 2 times this, and so that's the maximum number of times. So, that is the maximum number of steps that I have to traverse, and each time at each step I have to do a division, and that is something that I am not discussing in the lecture, but it is more or less well known that division and multiplication require the same number of steps. Therefore, I multiply here by square. So, I have something like log p to base 2 cube. Instead of, let us say, you may have some extra terms over here, that does not matter. It may have some extra terms because of doing for few times and like that, but it will be a small constant. Now, what was potentially possible is that if we go one step by step, so potentially instead of log to base 2, this could have been p many steps, and that would have been a disaster, because then we would not have been able to compute or decide the greatest common divisor or compute the inverse, but we can do that. So, in this slide I have given a very rough and definitely overestimation of the number of steps. There are fast algorithms to compute multiplications, there are fast and the other some other processes, and therefore we can make it faster, but we are sure of one thing, that the number of steps is not going to be more than a small constant times log p cube. So, if we look at the RSA algorithm now, we have come somewhat towards the middle. We have come up to just before the encryption, and the encryption is now exponential and taking the modulus. Now, then here we are going to have problem again, because again a is a large number, b is a large number, and x is a large number. So, if I am raising x to the power b, it's offhand it seems that it is going to take quite considerable time. So, now we come to the complexity of exponentiation. So, we have to compute ek and dk, both are exponents. For that, we have another algorithm which is called square and multiply algorithm. Now, I will discuss the square and multiply algorithm now, and in the problem sessions we will discuss how to use square and multiply algorithm in details. But now, square and multiply algorithm, our goal is to find out x to the power b, where x and b both are potentially very large numbers, and then reduce modulo n. Here we should remember that x to the power b mod n is congruent to x mod n to the power b mod n. So, it is immaterial whether we are doing modulus, that is we are reducing modulo in each step or afterwards, and one very reasonable thing that we can do is that we can always reduce modulo n, and reducing modulo n essentially does not take much time because it is one division. So, we can do that, but then what we do is that instead of B itself we take the binary representation of B. Let us see how it will look like. So, we will have B is equal to sigma I equal to 0 to L minus 1 of Bi 2 to the power I. So, for example, if B is 9, then this is going to be I equal to 0 to 3 Bi 2 to the power I, and let us try to find out Bi's. So, it is going to be B3 2 cube plus B2 2 square plus B1 2 plus B0, and where this is B3 into 8, B2 into 4, B1 into 2 plus B0, and it is not difficult to see that it is essentially 1 into 8 plus 0 into 4 plus 0 into 2 plus 1. So, this is the binary representation. So, this is how we are writing B, and then we introduce a one variable z, and this z is set to 1, and now we go into a loop. In this loop we start from L minus 1. So, in this case we will start from 3, go down to 0, and each time when we go in we square z. Initially z is 1, so we square it. We square z and take modulo n, because we are determined to reduce the size of the number we are handling at each step. So, we take modulo n, and after that we go here, and then we are checking this one. Here there is a misprint. It's going to be, it's not Ci, but it's Bi. That's fine. So, I'll write this step over here. There is a misprint over here. So, in that step it will be if Ci is equal to 1, if Ci is equal to 1, then Z goes to Z into X, and you can as well do mod n over there. So, I have said that you will keep on doing mod n. So, please remember that it is not Ci but Bi. So, what I am doing over here is that whenever I am checking this, I am checking the I corresponds to this loop variable, whatever I is set to, we are checking this, and if this is 1, I am multiplying x to z and storing z over here and keep on going into the loop down to 0. When I come to 0, I end there, and that z is my number. So, what I will suggest is that please try this algorithm, of course by changing the Ci to Bi. Try this algorithm after the lecture, see whether it works or not, and we will study this algorithm, we will work out examples in the discussion sessions of this lecture series. So, that is end of today's lecture. Thank you.